Welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 893, Groups of Special Equivalent Strings. This problem challenges us to analyze and group strings based on specific transformations, testing our understanding of string manipulation and data structures. Let's dive in. In this problem, we are given an array of strings called words, where each string consists only of lowercase English letters. Our task is to group these strings based on a specific condition known as being special equivalent. Two strings are considered special equivalent if one can be transformed into the other by performing a series of swaps. These swaps are constrained to either even-indexed characters or odd-indexed characters. For example, A, B, C, D, and DAB are special equivalent because we can swap A and C to get CBAD, and then swap B and D to get DAB. Similarly, ABCD is special equivalent to itself because no swaps are needed. However, ABCD and ABC are not special equivalent because no sequence of allowed swaps can transform the first string into the second. Once we identify which strings are special equivalent, we need to determine how many distinct groups of such strings exist in the array. Now let's discuss the input and output formats. The input is an array of strings called words, where each string is made up of lowercase English letters. The output is a single integer that represents the number of distinct groups of special equivalent strings in the array. To understand this better, let's look at an example. Suppose words equals ABCD, DAB, BAD, XYZZ, ZZXY. The output for this input is 3. Here's why: the strings ABCD, DAB, and CBAD all belong to the same group because they can be transformed into each other using the allowed swaps. Similarly, XYZZ and ZZXY form another group because they are special equivalent to each other. Finally, there's no other string in the array that matches either of these two groups, so we end up with 3 groups in total. Breaking this example down further, the first group consists of ABCD, DAB, and CBAD, as they can all be transformed into each other. The second group includes XYZZ and ZZXY, which are also special equivalent. Importantly, duplicate strings like ABCD within the same group do not count as additional groups. In another example, if words equals A, B, C, C, the output is also 3. Here, A forms one group, B forms another, and C forms the third. Even though A and C appear multiple times, duplicates don't create new groups. The key takeaway is that we're identifying distinct groups of special equivalent strings, not counting individual occurrences. Finally, let's review the constraints and edge cases. The length of the words array can range from 1 to 1000, and each string within the array can have a length between 1 and 20. All strings consist of lowercase English letters. One edge case to consider is when all strings in the array are identical. In that situation, there will be only one group. Another edge case is when all strings are unique and have a length of 1. In that case, since no two strings can be special equivalent, the number of groups will equal the length of the array. It's also important to note that strings of different lengths can never be special equivalent because the swapping operations depend on characters at even or odd indices, which are defined relative to the string's length. These constraints help guide us in designing an efficient solution to the problem. To start, we considered the brute force approach, which revolves around directly comparing all possible permutations of strings to identify groups of special equivalent strings. The intuition here is straightforward: if two strings are special equivalent, we can simulate all possible swaps of even-indexed and odd-indexed characters and compare the resulting strings. By applying this to every string in the provided array, we can group together those that are equivalent. However, the steps reveal the computational cost. Generating permutations for each string is factorial in nature, and comparing every string with others requires quadratic time. This results in an overall time complexity that grows too quickly to be practical for larger datasets. While simple to understand, the trade-off is clear: this method becomes infeasible for larger inputs due to its exponential growth and complexity. Instead of relying on brute force, we can adopt a more optimized approach using canonical representation. The key intuition here is that special equivalent strings can be identified by sorting their even-indexed and odd-indexed characters separately. This insight eliminates the need to simulate swaps directly. The first observation is that the even-indexed characters in a string can be rearranged independently of the odd-indexed ones, and sorting these subsets gives a unique identifier for the string's equivalence group. To implement this, we split each string into its even and odd indexed characters, sort both subsets, and combine them into a single canonical representation. By storing each unique representation in a set, we can efficiently determine the number of groups, as the size of the set corresponds to the distinct groups of special equivalent strings. Analyzing the complexity of this optimized approach, splitting a string into even and odd indexed characters takes linear time, or O(n). Sorting the two subsets introduces an O(n) log n complexity per string because of the sorting step. When we account for m strings of length n, the overall time complexity becomes O(m*n log n). This is significantly more efficient than the brute force approach, especially for larger datasets. The trade-offs here are minimal. While sorting dominates the runtime, the pre-processing step is still manageable within the given constraints. Additionally, an alternative method we considered was frequency counting. Instead of sorting, we could count the frequency of characters at even and odd indices, which avoids the sorting overhead. By storing these counts in a tuple as the canonical representation, we can achieve equivalence grouping in a similar manner. This method further reduces complexity, but introduces a slightly more complex implementation. With the frequency counting approach, the complexity of counting characters is linear, or O(n), for each string. For m strings of length n, the total time complexity is O(m*n), which is faster than the sorting-based approach. However, this method may require more memory to store frequency arrays, and the implementation is somewhat less intuitive compared to sorting. After evaluating both methods, the sorting-based canonical representation stood out as the preferred strategy. While frequency counting offers slightly better performance, the clarity and simplicity of sorting make it easier to implement and debug. Additionally, sorting avoids the factorial growth of the brute force method, striking a good balance between efficiency and maintainability. Sorting-based canonical representation does come with some trade-offs. Sorting introduces an O(n) log n complexity per string, which is slightly slower than the O(n) complexity of frequency counting for very large datasets. However, given the problem constraints, this trade-off is acceptable in practice. The sorting-based approach is straightforward to implement, minimizes the risk of errors, and provides an efficient solution within the constraints. In conclusion, this method offers the best balance between ease of implementation and performance. It avoids the inefficiency of brute force while remaining practical and intuitive, making it the most suitable choice for solving this problem. The problem involves grouping strings that are considered special equivalent. Two strings are special equivalent if, by repeatedly swapping characters at even indices or odd indices, we can make them identical. For example, given the strings A, B, C, D and CBAD, they are special equivalent because swapping the even-indexed characters at NC and the odd-indexed characters B and D transforms one into the other. The task here is to determine how many unique groups of special equivalent strings can be formed from a given list of words. Now, instead of simulating all possible swaps, which could be computationally expensive, we use a key insight to simplify the process. Each string can be represented by a normalized form. This is done by splitting the string into characters at even indices and characters at odd indices, sorting each group, and then concatenating these sorted groups to create a signature. For instance, the string ABCD has even-indexed characters at NC, and odd-indexed characters B and D. After sorting, these become AC and BD, and the resulting signature is ACT. Similarly, for CBAD, the even and odd characters also sort to AC and BD, giving the same signature ACT. Strings with the same signature belong to the same group. This approach allows us to efficiently identify and group special equivalent strings. The algorithm for solving this problem builds on the idea of normalized forms. First, we create an empty set called unique_signatures to store these unique normalized forms. For each string in the input list, we separate the even-indexed and odd-indexed characters, sort them, and then combine them to form a signature. This signature is then added to the set. The size of the set, after processing all strings, represents the number of unique groups of special equivalent strings. Sorting ensures that all permutations of swaps are accounted for in the signature, while the set automatically eliminates duplicates, making the process efficient. The complexity analysis of this algorithm shows it to be efficient given the constraints. For each string of length n, separating the characters into even and odd groups takes O(n). Sorting these groups takes O(n) log n. Combining the groups into a signature and adding it to the set takes O(1). For a list of m strings, the total time complexity becomes O(m*n log n). Regarding space complexity, the set requires O(k) space, where k is the number of unique signatures. Additionally, the temporary space for storing even and odd characters is O(n). Thus, the overall space complexity is O(k plus n), making the algorithm efficient in both time and space. To see the algorithm in action, consider the input array of words ABCD, BAD, XYZZ, ZZYX. We initialize an empty set called unique_signatures. For the first word ABCD, the even indexed characters are A and C, and the odd indexed characters are B and D. After sorting, these become AC and BD, forming the signature act, which we add to the set. For the next word QBAD, the even and odd characters also sort to AC and BD, resulting in the same signature act. Since this signature already exists in the set, it is not added again. Moving to XYZZ, the even characters are X and Z, and the odd characters are Y and Z. After sorting, the signature becomes XZZY, which is added to the set. Finally, for the word ZZYX, the even characters are Z and Y, and the odd characters are Z and X. Sorting these gives YZ and XZ, and the signature YZXZ, which is added to the set. At the end of this process, the set contains three unique signatures, ACT, XZZY, and YZXZ. Therefore, the number of unique groups of special equivalent strings is the size of the set, which is 3. This result is returned as the output. This solution determines the number of groups of special equivalent strings by leveraging the properties of even and odd indexed characters. First, a set unique_signatures is initialized to store unique representations of each group. Each string is processed individually by splitting it into its even indexed and odd indexed characters using slicing, word, :2, for evens and word, 1, 2, for odds. These characters are then sorted, as their arrangement within even or odd indices does not affect special equivalence. The sorted even and odd characters are combined into a tuple signature, which uniquely represents the strings group. This signature is added to the unique_signatures set, ensuring duplicates are ignored. Finally, the size of unique_signatures is returned, which corresponds to the number of unique groups. The time complexity of this approach is O(n*m log m, where n is the number of strings and m is their average length, due to the sorting step. This implementation is efficient and handles all edge cases, such as strings of varying lengths and duplicate inputs, seamlessly. Here, we start by importing the necessary utilities and defining our solution class. The main method of interest is number special equiv groups, which takes an array of strings called words as input. To keep track of the unique groups of special equivalent strings, we use a hash set called unique signatures. Next, for each word in the array, we separate its characters into two groups based on their indices, even indexed characters and odd indexed characters. This is done using two string builder objects, evenchars and oddchars. The loop iterates over each character in the word, and depending on whether the index is even or odd, the character is appended to the appropriate string builder. Once the characters are separated, we convert them into character arrays and sort them alphabetically. At this stage, we have two sorted arrays, one for the even indexed characters and another for the odd indexed characters. Next, we combine the sorted even and odd character arrays to create a unique signature for the current word. This signature is a concatenation of the two sorted arrays, ensuring that any word with the same character composition in even and odd positions will produce the same signature. We then add this signature to the unique signatures set, which automatically handles duplicates. After processing all the words, the size of the unique signatures set gives us the total number of unique groups of special equivalent strings. Finally, we return this size as the result. This approach ensures that we efficiently group words based on their special equivalence by leveraging the properties of sets and sorted character arrays. To solve this problem, we start with the first example where the input words are A, B, C, A, C, and C. The goal is to group words that are special equivalent. First, we initialize an empty set called unique_signatures to store the unique signatures of the words. Now, for the first word A, we separate its even indexed characters, which is A, and its odd indexed characters, which is an empty string since there are no odd indices. After sorting these two parts, the even indexed part remains A, and the odd-indexed part remains empty. This gives us a signature of a. We then add this signature to the set, so our unique underscore signatures is now a. Next, we process the word B. Its even-indexed characters are B, and its odd-indexed characters are empty. Sorting these gives the signature B, which is added to the set, making unique underscore signatures equal to a B. Now we process the word C. The even-indexed characters are C, while the odd-indexed characters are empty. After sorting, the signature becomes C, which is added to our set, updating unique underscore signatures to a B, C. For the second occurrence of the word a, its signature is computed as a, again, which is already present in the set, so no changes are made. Similarly, for the second and third occurrences of the word C, their signatures are also C, which are already present in the set, so unique underscore signatures remains unchanged. At this point, no new signatures are added, and the set continues to hold a B, C. Finally, for this example, we count the total number of unique signatures in the set. These signatures are a, B, C, so the total number of groups is 3. Moving on to the second example, the input words are ABCD, DAB, AD, BAD. Again, we initialize the unique underscore signatures set as empty. For the first word ABCD, the even-indexed characters are AC, and the odd-indexed characters are BD. Sorting these gives AC for the even part and BD for the odd part, resulting in the signature AC, BD. This is added to the set, so unique underscore signatures becomes AC, BD. Next, we process the word DAB. The even-indexed characters are CA, and the odd-indexed characters are DB. After sorting, the even part becomes AC, and the odd part becomes BD, giving the signature AC, BD. Since this signature is already in the set, no changes are made. Then, for the word AD, its even-indexed characters are UB and odd-indexed characters are DC. Sorting these gives AC for the even part and BD for the odd part, resulting in the same signature, AC, BD, which is already present in the set, so no updates are needed. Finally, for the word QAD, the even-indexed characters are CA, and the odd-indexed characters are BD. After sorting, we again get the signature, AC, BD, which is already in the set, so there are no changes. At the end of this example, the set of unique signatures remains AC, BD. The total number of groups for this input is therefore 1. Now, let's consider the third example, where the input words are ABC, ACB, BAZ, CAB, CBA. As usual, we start by initializing an empty set for unique underscore signatures. Processing the first word ABC, we find that its even-indexed characters are AC, and its odd-indexed characters are B. Sorting these gives AC for the even part and B for the odd part, resulting in the signature AC, B. This signature is added to the set, so unique underscore signatures is now AC, B. For the word ACB, the even-indexed characters are UB, and the odd-indexed characters are C. After sorting, the even part becomes AC, and the odd part becomes B, yielding the signature AC, B. Since this signature is already in the set, no changes are made. Similarly, for BAC, the even-indexed characters are BC, and the odd-indexed characters are A. Sorting results in the same signature, AC, B, which is already in the set, so no updates are needed. The word CA has even-indexed characters BA and odd-indexed characters C. Sorting these gives AC and B, which again results in the signature AC, B. As this is already present, the set remains unchanged. Finally, for the word CAB, its even-indexed characters are CA, and the odd-indexed characters are B. After sorting, we get the signature AC, B, which is already in the set. For the word CBA, the even-indexed characters are CB, and the odd-indexed characters are A. Sorting these again gives the signature AC, B, which is still present in the set. At the end of this example, the unique signatures in the set are AC, B, meaning there is only one group of special equivalent strings for this input. This concludes the solution walkthrough for this problem. To analyze the time complexity of our solution, let's define n as the number of words in the input list and k as the maximum length of a word. The first step is iterating through each of the n words, which results in n iterations. For each word, we separate the even and odd indexed characters using slicing operations like word, 2, for even characters and word, 2, for odd characters. These slicing operations are proportional to the length of the word, making them OK for each word. Next, we sort the even and odd characters independently. Since sorting dominates in terms of time complexity, this step takes k log k for each word. After sorting, we create a tuple from the sorted even and odd characters. Constructing this tuple is an O1 operation, as is inserting it into a set under the average case. Combining all these steps, the time complexity per word becomes OK for slicing, k log k for sorting, and O1 for tuple creation and insertion. Sorting dominates, so the total per word complexity is k log k. Now, when considering all n words in the input list, the total time complexity becomes n asterisk k log k, which simplifies to k log k. This time complexity remains the same across best, average, and worst cases because every word must be processed fully regardless of its content. Shifting to space complexity, the main contributor is the unique signatures set, which stores at most n unique signatures. Each signature contains 2 sorted strings, each of maximum length k, leading to a space requirement of n asterisk k. Additionally, temporary space is used during processing. For slicing the even and odd characters, we need k space per word. Sorting the even and odd characters also requires k additional space due to the sorting algorithm, such as timsort. Combining these, the temporary space required per word is k for slicing and k for sorting, which adds up to k. However, since this temporary space is reused for each word and does not accumulate, it does not affect the overall space complexity. The total space complexity is dominated by the unique signatures set, which is n asterisk k. This efficient use of space is a significant improvement over a brute force approach, where we would directly compare all pairs of words. The naive comparison of all n words with each other would result in a time complexity of n squared asterisk k due to the pairwise comparisons. This brute force approach is much less efficient than our optimized solution, which achieves n k log k by avoiding pairwise comparisons. Instead, we generate a unique signature for each word, enabling efficient grouping using a set. Sorting the even and odd characters guarantees that words with the same signature are grouped together, achieving the desired result without redundant comparisons. To summarize, the optimized approach has a time complexity of n k log k and a space complexity of n asterisk k. This is significantly faster and more space efficient than the brute force approach, especially when dealing with large inputs. By leveraging sorting and set operations, the solution is able to handle the grouping in a clean and efficient manner. When tackling this problem, there are several common mistakes to watch out for. First, one frequent error is confusing the even and odd index groups. For example, if you mistakenly swap characters between these groups, it violates the problem's constraints and will produce incorrect results. Make sure you carefully separate indices based on their parity, using zero-based indexing. Another issue to be mindful of is overlooking edge cases. Scenarios like single character strings, strings where all characters are identical, or strings that don't permit any valid swaps can easily trip up your solution. It's crucial to include these in your test plan to avoid surprises. Inefficient sorting is another pitfall. Sorting the substrings repeatedly within loops can drastically increase the time complexity of your solution. Instead, focus on minimizing redundant operations. Additionally, misunderstanding character grouping can cause mismatches during comparisons. Always double-check that even and odd characters are grouped correctly. Finally, hard-coding specific test cases without considering general patterns can lead to failures on unseen inputs. Aim to test a diverse set of examples to ensure your solution is robust. Understanding the insights behind this problem can greatly enhance your approach. One of the key skills being tested is your ability to recognize patterns and invariants in permutations. A useful insight here is that you only need the order of the sorted even-indexed and odd-indexed characters to determine equivalence between strings. Efficiency is another critical factor. While brute force solutions might work for small inputs, they become impractical for larger constraints. Interviewers often expect you to come up with solutions that are optimized to O, n, or O, n log n. It's also important to clarify the problem statement whenever you're unsure about the input conditions. For example, if the problem doesn't explicitly state whether all input strings have equal lengths, ask the interviewer to confirm. Lastly, consider the trade-offs between different approaches. While a brute force method might seem intuitive, hashing or sorting-based techniques are much more efficient. Be ready to discuss these trade-offs, as understanding them demonstrates both your problem-solving skills and your awareness of algorithmic efficiency. This problem shares similarities with a few other LeetCode problems that you might find helpful to study. For example, LeetCode 49, which involves grouping anagrams, or LeetCode 917, which focuses on reversing only the letters in a string, both have overlapping concepts. Other related problems include LeetCode 438, where you find all anagrams in a string, and LeetCode 3, which deals with finding the longest substring without repeating characters. Now, let's discuss the alternative approaches you can use here and their trade-offs. A sorting-based approach involves separating the even-indexed and odd-indexed characters, sorting each group, and comparing them. This approach has a time complexity of O, n log n, due to the sorting step. While this method is straightforward, the sorting operation adds overhead compared to other approaches. Alternatively, a hashing-based approach creates a unique signature for each string by sorting the even and odd characters and then storing these signatures in a hash set or hash map. This method, with a complexity of O, n, is more scalable for larger inputs but requires additional space for the hash storage. Finally, there's the brute force approach, where you simulate all possible swaps and directly compare results. While simple in concept, this approach has a factorial time complexity of O, n, making it impractical for larger input sizes. Each method has its strengths and weaknesses, so understanding where to apply them is key. Great job! We've successfully walked through the solution to groups of special equivalent strings. This problem highlighted the power of string manipulation and hashing for grouping tasks. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!